Hello. So I'd like to finish first talking about the exercise we did on Friday with the Towers of Hanoi before I move on to any new content. Now there were a couple of groups that got this, but I want to make sure that everybody understands how this works because this is a perfect example of how we can use recursion to break down what seems like an insanely complicated problem into a plan that the computer can follow with only a few lines of code. This is the magic of recursion. Something that seems insane, you can kind of plan it out with a few lines of code and the computer gets it for you, fills in all the details. Okay? So our general strategy was to say, well, I don't know how to do this, but let me assume that I do know how to do a slightly smaller version. So if I have 4 disks and I need to move them from the source peg to the target peg, then I'm going to assume that I know how to move 3 disks from one peg to another, and I can use that as a subroutine to solve the 4-disk problem. Okay, so in particular, I'm only supposed to move one peg at a time, but let me assume that somehow I knew how to move this whole chunk of 3 from the source peg to the free peg. Okay, so I move these 3 disks from the source peg to the free peg. That definitely took more than one step. I don't know how it happened, but let me just assume I can do it. All right. So now that makes room for the biggest disk that I have to move from the source to the target. So let me go ahead and move that disk now. So that's kind of the second step here. Okay, great. Now I can finish because, again, I'm assuming that I know how to move 3 disks. So they're on the free peg, but let me move them from the free peg to the target peg. And now they'll be on top of the big one, and now we got the full stack over there. Very good. All right, so that's how we do it. That's all there is to it. Okay. But how do we write this in code, and how does it then show us the full solution? So let's go to the code here. And so what I did was, okay, I made this Hanoi class, and it says how many disks there are. It starts off by putting all the disks on the left stack. So I have 3 stacks. Each stack represents a different peg. So I got a stack on the left, a stack in the middle, and a stack on the right. And the reason that the stack is the right data structure for this problem is because we can only push and pop from the top. We can only take the disks off of the top of each peg. So the stack is a perfect data structure for this. And just to tell you what it's storing, well, it represents the pegs. Represents the each stack represents the disks that are on it as numbers. So this green disk would be a 1, this yellow disk would be a 2, this red disk would be a 3, and this blue disk would be a 4. So that's what's stored on the stacks. Okay. So we push starting at n down to 1 so that we end up on the left peg with the smallest disk on top and the largest disk on the bottom. That's how we started off. Okay, great. So we've initialized this problem. Now we want to solve it and show the solution. So we're trying to do more than what we did in just counting the solution, which I had you do in the module. Now we actually want to show each step. Okay. So a common thing that you do with recursion is you have a method that kicks it off, and then you have a more general recursive method that is able to handle the smaller recursive steps. So how am I going to kick this off? All right, so my recursive method takes in 4 parameters: a source peg, a target peg, and a free peg. So the free peg is kind of my staging area. And also the 4th parameter is the number of disks I want to move off the top of source onto target. Okay. So I start the recursion by saying, hey, you know what? I actually want to move all the big N disks from the left peg to the target, which is the right peg, and I can use the middle peg as the staging area. All right. So let's see how I can translate what I did in this picture over here into some code. So in general, we're trying to move the top little n disks from a source stack to a target stack. And we're allowed to use the free stack as a staging area to do intermediate things. So what I'm going to do is just like when I had a problem with 4 disks that I moved 3 out of the way, I'm going to start by moving n minus 1 out of the way onto the free peg. Okay, so I'm going to move n minus 1 disks out of the way onto the free peg. Alright, so I can do that in the picture here. How do I do that in code? Well, actually I'm going to make a recursive call. So with recursion, what you should think is, hey, I don't know how this is going to happen, but recursively let me assume that I can accomplish this. The recursive calls will magically take care of it, and then I just have to say how to combine it. Okay. So I say self.solve recursive. So I'm going to move the top n minus 1 disks from the source to the free stack. Okay, right? So actually my target is free on this recursive call. So this is where it gets a little interesting, because I'm swapping the role of free and target here. Free now becomes actually what I want my target to be, which means by process of elimination, for these 3 disks, I can use the target as the staging area. Okay, and I'm trying to move the top n minus 1, not all n, just the top n minus 1 from source to free, which means by process of elimination that I can use the target peg as my staging area. Okay, so see how I actually flip these 2 parameters. So that's part of the magic, that's part of the trick here. Okay, so once I move these top n minus 1 from the source to the free peg, I know that I've made room to move my nth disk from the source to the target. So let me do it. So I made enough room now to move disk n from source to target. Okay. Now here's where we can actually use the stack data structure. This is where the real work happens. I didn't do any real work so far, I just kind of did some planning, right? I said, you know, I'm going to plan to move these n minus 1 pegs out of the way, but now I actually am going to move a big peg from the source to the target. So here's where I go to the stack API and I say, okay, what do I got? Well, I can pop off the top and I can push onto the top. So let me pop off of the top of the source this disk. Okay, so I'm going to pop that off. That's going to return that disk. And then I want to push that onto the target. All right? So that's it. But this is where the motion actually happens. This is where we're doing work of moving the disks around. So I'm actually going to draw the result of doing this. So I have a method up here called drawFrame, which is going to make an image which shows the state of these 3 pegs at any point in time. It's going to save that image to the hard drive. And this is where I want to update that. So now I'm going to say self.drawFrame at that step. All right, cool. So I just did that. Excellent. So what do I have left to do? Well, I've got to move the free disks. I've got to move the n-1 that I got out of the way. They're on the free peg. From the free peg to the target. And then I'm done. Okay, so how do I move these from the free to the target? Well, another recursive call. So move n-1 disks from the free peg to the target peg. So now I'm going to plan to move things from the free peg, so that's my source peg now, to the target peg. And by process of elimination, that means that I can use my source peg as the staging area in between. Okay, so I move the top n-1 from the free peg to the target peg, and in between I can use the source peg as my staging area. And that's it. Now, am I done? Is that it? Did I just write 4 lines of code and solve this whole darn thing? Okay, but I should hear somebody screaming. Do I hear somebody screaming? Stopping condition? Infinite recursion? Catastrophe? Okay, so watch out, right? Because this will keep going forever if you're not careful. You have to have a stopping condition. And the stopping condition is that if I have fewer than 1 disk to move, then I should be done, right? If I don't move anything, then I shouldn't keep trying to move things. So I'll say only if n is greater than 0 do we actually do this. Okay, if we're asked to move 0 disks, just don't do anything. Okay, that'll keep this from going into infinite recursion. Okay, so let's try to run this. So let me go and see. This should output a bunch of images. So I'm going to do, let me start with a slightly smaller one. I'll start with Hanoi of 3. So 3 disks on the left one starting with. Okay, so I'll write in this Python Hanoi.py. Did I get it? Let's see. Okay, so 0. Okay, so this is the beginning. First step, it moved that there. Second step, it moved that there. Okay, there we go. Seemed like that worked. So that took 7 steps. Let's go to 4. If you remember, this should actually take 15 steps. It's 2 to the number of disks minus 1, which we'll prove in the very next video. But for now, we can take that for granted. So let's see. Okay, cool. Yeah, outputted 15 steps here. Now look at them. I see boom, 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 boom. It's like magic to watch this actually happen. Okay. Let's jump up a little bit. Let me solve 8. This will be huge because this will be 2 to the 8th, which is 256 minus 1, so 255 steps. Let's do it though. All right, so let's see how this one works. So I'll just start to look through here. All right, so kind of cool. It got this one to move over there, but looks like it's going to have to move that one there. Okay, now I've got that big disk there. Okay. So remember, this takes 256 steps. So at some point, I'm trying to get the top 7 disks to the center one. So that should happen about halfway through, or a third of the way through. No, halfway through. Let's see. So 256. So once I get around 127, 128, I should see. Okay, yeah, good. So step 127, I see that. Right, that's how big how long it takes to move 7. So I've moved those out of the way. Now I can move the big one. Okay, but guess what? I got to do all that again. This time I can use the left peg as my staging area and make all that stuff happen. And eventually I end up solving it in 255 steps as promised. Wonderful. Okay, look. So that was only, in the end, okay, if you include the if statement, 5 lines of code. That's dope. Okay, 5 lines of code to do this really pretty complex stuff. Now, of course, yeah, I wrote some code to draw stuff, but this code is just kind of boilerplate. I'm drawing things, whatever. The meat of the work happens with only 5 lines of code, and recursion just does it for us. Beautiful. All right, so and now we're going to move on to new content. In the next video, I'm going to talk about proofs by induction, which is how we know exactly how long this is going to take. Okay.